All right, shall we begin? Shh, we're going to start now. It's very important. So we've got the new technology going on because of the YouTube recording from last time. It was, I don't know if anyone listened to it, because why would you? Because you're here. Was kind of warbly. So this new setup, I think, works better. And yeah, we've got all the bars going well. So once again, if you want to review the lectures, just go to the YouTube playlist, and they'll all be there. I got to find new ways of shaming late people. Not really late, though. It's exactly on time. Any questions from last time? Last time was pretty vague, very introductory. We're still in introduction mode. So today is going to be also very, very light. And very often, the lectures will end quite early. Like, I don't believe in going on and on forever. So if I can get it done in 20 minutes, I'll get it done in 20 minutes. But sometimes we'll go the full 90. But very often, maybe 30, 45. So my philosophy is I will teach you the thing, maybe do one example, but we won't go on and on with examples. I leave it to you to go home and do the examples yourself. So this room is for theory and content, and practice is for your own time. So a lot of stats classes, I find, the bulk of it is taken up with endless examples. And nobody wants to be here, right? So let's make it fast. I can't believe I said that on the record. I keep forgetting. I'm being recorded all the time now. No, every lecture will go full 90 minutes, as far as the university knows. All right, so no comments or questions or concerns from last time. Good. The labs begin next week. Are you Mondays or Wednesdays? What's this class? Mondays. Okay, I think everyone's on Mondays. All right. So I think the first week there is no lab assignment. You just show up and get used to the room and the login process and meet the TA. And the week after that, we'll start the official lab assignments, which are being marked. Okay. So that way you got a chance to be late once and to mess up once and all that great stuff. So I think I mentioned the buddy program last time. If I didn't, I want to remind you of it. I think most of you were in first year last year, so you probably were introduced to it then as well. But we're running it again. What it is, if you don't know, is a kind of mentorship program. We don't like to use the word mentoring because it isn't mentoring. There's a separate mentoring program. This is more of a social engagement program to help the first year students enter into a life of university stress and excitement. And so what we do is we attach first-year students with a handful of upper-year students. If you'd like to volunteer as an upper-year student who gets attached to a first-year student, sign up. So go to the website, which is there, and sign up, put your name in there, and we'll let you know when the first meeting is being held. It'll be in October. And this year, Sonia Galati is running it because I don't have a lot of time. Any questions about the buddy program? Okay, it's a lot of fun. You know, it's not really stressful. You just hang out and do things, and it's volunteer hours. If you want to, you know, check that off on your CV as something you've done, it works. Okay, so I want to talk to you a little bit about evidence-based medicine or evidence-based practice, EBP or EBM. Have you heard that term before, evidence-based medicine? You haven't? Okay, that's good. It is really the defining trait of modern medicine these days, evidence-based medicine. You may ask yourself, if it's not evidence-based, then what is it? Well, historically, the practice of medicine and things related to medicine, clinical care, have not been based on evidence. They've been based on what you were told. So we have a lot of stuff, a lot of therapies that are being funded and people engaged in that really don't work. And it's really hard getting rid of them because they're inculcated into the culture of medicine. And a lot of what we do in statistics and epidemiology is to attach a measurement of efficacy to various therapies to determine if, in fact, they are working. So I'll give you an example. When I was a PhD student, one of my first jobs was working with an obstetric group in London that was trying to look at whether or not obstetrical care around women who are about to give birth was meaningful and efficacious. So some of the things they would do is they'd give you an enema before you give birth, or prevent your family from being in the room with you with things, or surround you with clinicians just in case of infection issues. And what we found was none of that stuff matters. So the enema doesn't seem to improve your outcomes at all. Having their family in a room with you actually is better for you, and things like that. And the problem is, when it came time to communicate these findings to the obstetricians, there was a cultural barrier preventing them from accepting the wisdom. So we engaged in an outreach program with all these doctors. Like, look, you should let them, home births, they're mostly okay. You should let the family in the room with you, let the lights down low, forget the enema, whatever it might be, open the window, all that stuff really makes them feel better and doesn't affect the outcomes that much. But the culture did not change for another 20 years. Now, of course, have family in the room with you is quite common. Back then it wasn't. So the point I'm trying to make is, even though we have evidence for why some things can work well and some things don't, really the defining trait in whether or not you do something as a doctor is what your mentor told you. Right, so the culture changed a field. So when we engage in evidence-based medicine or evidence-based practice, we're looking for the best possible evidence to inform a decision. Like, should I be, if I'm a diabetic, should I be on insulin now or should I wait 6 months? Something as simple as that. Well, what does the evidence say? What do the papers say? The studies say? There's a process for finding the best possible evidence. And that process actually begins with assessing the quality of the statistics used in the various studies. Were they appropriate? What do they find? Do they find significance? Were they under or overpowered? And you'll know what those words mean in a few months, hopefully. So some of the things we ask when we do an evidence-based medicine search is, can you see that well, by the way? Should I turn on the light? Is that all right? Let me see if should I mess with this at all? Can I mess with this at all? I'm a little scared. Yeah, better? Right on, okay. So how reliable is the evidence? Reliability can mean many things. Specifically here it means is how reproducible is it? Is this a one-off, or is it something we should expect all the time? The magnitude of effect. So maybe we find that if you take insulin, rather than wait 6 months to see if you get better, you have like a 0.01% greater chance of surviving into your old age. Is that a big magnitude? It depends on your perspective. So the magnitude is important. And how precise is the estimate? And precision we will talk a little bit about later on as we measure what's called confidence intervals. Have you heard the term confidence intervals before? Yeah. Okay, good. All new things for you. A confidence interval really is the statistical measurement of precision that will take you into your career, and we will get to that in a few weeks. And so answering these questions all require a fundamental understanding of statistics. Now, I mentioned some of this stuff last time. We'll go over it again just very quickly. Data is what you collect in the course of your investigation. If I ask you what all your names are, that's data. If I look through your marks at the end of the year, that's data. When I process that data, I acquire wisdom that I can make conclusions from. When I attach context to that data, I get information. Right? And we mentioned that there's quantitative and qualitative data. If I ask you how you're feeling today, you say, I'm feeling okay. That's qualitative data. If I ask you to rank on a scale of 1 to 10, how are you feeling today? That's quantitative data. And very often we can move between the two, not a wise thing to do. But recognize there are these two different universes of data. We mentioned last time as well is an independent variable and a dependent variable. The independent variable is the exposure or the behavior or the thing that's free to be whatever it wants to be, and the dependent variable is the result of that independent variation. So whether or not you smoke, that's an independent variable. Whether or not you get cancer from smoking, that's dependent on whether or not you smoke. Okay, so really keep that distinction in your mind. That's going to dictate a lot of how we choose analyses and which variables go in which equation. I keep forgetting what the sequence of courses are in this program. Have you done your research methods class yet? No. Okay, so that's now a third-year thing. Okay. I think it used to be the way around. I'm not sure. So when you do your research methods class, you'll learn about how to phrase research questions. It's really important to phrase them well. And there are all kinds of models to use to phrase them well. It's not simply a case of, oh, I'm interested in cancer and smoking. That's a topic. A research question would be something like, you know, amongst women aged 25 to 30, is there a statistically significant association between the number of cigarettes smoked per week and the probability of contracting cancer within the first 10 years? Something very specific and measurable. So a research question is answerable using an analytical technique. Okay. This is not stuff you should be worried about taking down right now. I'm not testing you on this stuff. This is stuff with the background to prepare you for doing deep analyses later on. So in the research questions, we have a population that we care about, and we have research variables that we care about. So the example I just gave you, the population is women aged 25 to 45, whatever I said. And the variables are going to be smoking rate and probability of cancer. Or in this example here, in hospitalized children, does music reduce stress? And music here is the independent variable, and stress is a dependent variable. So I can modulate the amount of music they're exposed to as much as I want. It's independent. But whether or not they experience stress or have decreased stress, that's dependent on the independent variation of the music. Pretty clear, right? So here, this little concept here, a lot of students struggle with, and again, it's not critical that you understand this from the perspective of getting a good mark. It's important that you understand this from the perspective of understanding the role of analysis in your life. So when we have a variable, really defining it goes through two phases. The first is conceptual, and the second is operational. By conceptual, I mean, what is it we're trying to measure? I remember what measurement is. Measurement is assigning a quantity to a quality. And operational is, how are you going to define it? So the example I'll give you is age. So if I ask you how old you are, you'll probably say, oh, I'm 20, I'm 21, whatever it is. Okay, because you've been taught to express age as a matter of years measured from the point you emerged from your mother. Right? That's a very specific definition, even though you haven't thought about it. And in fact, you've already rounded it up or down. So if you haven't reached your if you're 21 and your birthday is next week, you're probably still going to say you're 21 up until next week, and you'll say you're 22, even though you probably should round up to 22. Right? So we have these cultural conditions that affect how we express the operational qualities of our variables. So a variable really is a bucket for putting data in it. The bucket very often does not express the fullness of what we're trying to measure. Okay. The other example I'll give you is the one earlier. If I say I have a variable called happiness that I will give to you to fill out in a survey. How happy are you today? Okay, that's a quality, your level of happiness. The concept of happiness, you're on YouTube now, it's hilarious. Up and down. The quality of happiness is, well, can you define happiness? I can't. You probably can't either. But there's a concept there. I want to know, are you upset to some extent? Maybe there's a purpose I'm asking. I want to know, are you going to be problematic in this class? I want to know, are you going to be doing poorly in this class because you're unhappy? Are you going to be acting out? Or maybe I care about you as a person. Unlikely, but maybe it's possible, right? So the concept there is what I mean to measure when I ask you about happiness. Our language is insufficient to the task. How I operationalize that limitation is where the statistics comes in. So I ask you about your happiness, rate it on a scale of 1 to 5, where 1 is miserable and 5 is ecstatic. Okay, so now I've operationalized this thing I called happiness, and I've created a variable out of it. But I hope you understand that that variable is limited. If I ask you to rate your happiness from 1 to 5, does that really tell me how you feel? It doesn't, does it? That's what we rely on. We rely on the bucket of the variable of the score of 1 to 5 to give the illusion of understanding what's in the data, your happiness. Okay? And we see this all the time. And again, it's not going to affect how you do in this class. But as you progress through your research careers, understand when you read results of analyses, the variables do not express truth. The variables express one aspect of an analysis from which you, the human animal, must then extrapolate to something resembling truth. There are limitations in every step of the research process. The very first limitation is how we operationalize our concepts that we're trying to measure. That was a long lecture on a really stupid little concept, but I hope you get the idea there, right? Cool. Moving on. I can move on? All right. So I just said the same thing, the same slide I said. Now we talked a little bit about descriptive statistics, I think, maybe. I gave my epidemiology class lecture yesterday, and we covered some of the same things, so I'm a little unclear what I said to who right now. So in descriptive statistics, what we care about is describing the content of my sample. You are my sample. You know, and again, I mentioned if I'm trying to extrapolate what I do with my sample to understanding the population as a whole, then describing you in many ways is the first step towards describing the experiences of the population as a whole. What I do with my sample allows me to infer qualities about my reference population. So descriptive statistics just summarize some aspect of your qualities. Example, the percentage of women in this class, the average age, average weight, and so forth. Inferential statistics, as I mentioned last time, is when I attempt to use what I've learned about my sample to infer qualities about the greater population. And as we mentioned last time, there are two terminologies I want you to remember: parameter and statistic. A statistic is a measurement of the sample. A parameter is a measurement of the population. Very rarely can we actually measure a parameter. All right, so let's say I am trying to measure, I don't know, the average age of all adults in Canada. That's a parameter. Okay, so if let's say I get a sample of adults from Ottawa, randomly selected, and I measure their ages, and I take the average, I can use that average to estimate the average age of all Canadians. That's what I typically do in inferential statistics. Is there a way for me to get the actual parameter of all ages of adults in Canada? Is there a way? Can you think of one? Whisper, 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 whisper. Yeah? Exactly right. I was waiting for that magic word, census. So that's why we have censuses, to have that kind of data. So we actually do know what the average age of all adults in Canada is taken at the last census. Right? So those are rare occasions when we have the actual parameter. But usually we don't have the actual parameter. We are using the statistics to estimate the parameter. As we will see when I give you the formulas for various statistical measures, we often assume that the statistic is the parameter. So the equation will say insert parameter here. We haven't got the parameter. I'm going to use my statistic instead to estimate the parameter. Okay. So that's a nuance. It doesn't affect the math. It doesn't affect the answer that you get. It affects how you interpret the results. So just keep that straight. So we talked a little bit about the statistical packages that you're going to be using. You're going to be using SPSS mostly. This is the statistical package for the social sciences. Has anyone used SPSS before? 1%. Great. Okay, so you have one expert you can appeal to if you get really stuck on things. And I mentioned you can buy a student version to play with at home if you want. I think it's like $20. I'm not sure. If not, you can download the evaluation version for free from IBM from the website. That'll last for a month or something. You can play with that for free, or you can wink, wink, get it from other sources that I won't tell you about because somebody will sue me. Right? So on the class website, I've already provided under lab assignments a few SPSS data sets, and these are the ones you're going to use for many of your lab assignments. So you can play with those as much as you like and practice on them as much as you like. So SPSS is friendly and user-driven, and menu-driven rather, and what I'm going to do occasionally is show you screenshots from SPSS on how to use it. Our textbook is built upon SPSS, so you can use examples from a textbook as well. In fact, the data sets I've taken from a textbook manufacturer to make this as seamlessly continuous as possible. So in SPSS, you get two views. You get a data view and you get a variable view. The data view shows you your data. So let's say I've done a study, I'm looking at, well, I'm going to look at all your marks at the end of the year, right? So I already have an Excel spreadsheet with all your names, all your ID numbers, your email addresses, what you get on your first midterm, what you get in the final, and what you get in your lab assignments. Okay, so that's a data set already. Most data sets are set up like an Excel spreadsheet. We call that a flat file, by the way. So as you move on to your research career, flat files, because there's no depth to them. If I had linked databases, like in Microsoft Access, those are relational databases. Relational databases are mixtures of flat files. Don't worry about that. I've got verbal diarrhea today. I'm telling you all things you don't need to know about. But an Excel spreadsheet is a flat file. And so the data editor in SPSS resembles an Excel spreadsheet. You're going to have the same thing. Each column represents a variable, and each row represents somebody in that variable, in that data set. So the first column will be, maybe it's your name, maybe it's your ID number that you got in your midterm, and so forth. And each row represents an individual person. So an important thing to consider when we talk about statistical analyses is how we are indexing our data. So what is the unit of analysis? In the example I just gave you, the unit of analysis is person. When I compute your average scores at the end of your midterm, I'm going to index you by person as well. Sometimes we haven't got that kind of nuance. So one of my grad students, he just completed his thesis, and we did an analysis of concussion rates amongst mixed martial arts fighters. And I bought a bunch of data from the UFC to do this. And the data came in such a way that each row didn't represent an individual, it represented a fight, it represented a mixed martial arts match. So each match had a fighter, the other fighter, how long it took, when it ended, how many shots were, all this stuff, right? But if we want to do an analysis by what's the average age of the fighters, we can't do it because each row doesn't represent a fighter, it represents a fight. We had to convert that data, it was painstaking, into different individuals. Now, if one guy has 3 fights, well, he's going to appear 3 times. That's confusing. So suddenly, if we're computing the average age of fighters, he counts 3 times. So you see how complicated this gets very fast. Right? We're not going to encounter that in this class, but recognize that this is one of the challenges in having clean data. Every data set you deal with, each row will be one instance, one individual, one appropriate unit of analysis to make your life easy. So that's the data view. The data view is like the Excel spreadsheet. The variable view has a list of all the variables in your data set and their attributes. So you'll see age will be one of the variables, and the next one will show, is it a continuous or categorical variable? Well, hopefully it's continuous. What are the ranges, and is there a label for? A label will be like the variable name could be age, but the label will be how old is this person for human usage, and so forth. So you'll play around with it and see how you can mess around. You can flip back and forth between the data view and the variable view. So this is the data view. Where's my pointer? I haven't got a pointer. Great. You can see that each row here represents a person in this data set, and these are the variable names: age, marital status, address, income. So what kind of variable is age? Whisper. What is it? Not dependent or independent. What measurement level? Remember, there's nominal, ordinal, ratio, interval. Remember all that stuff? What's age? Yeah? That's correct. And why is that? It has a real 0. Being 0 years old means something, and it's continuous. Being 55.5 means something. So in this case, age is a ratio level measurement. In SPSS, I don't know if ratio is an option. It might just be continuous. So marital status, married or unmarried, is our options. Is this what kind of measurement is this? What kind of variable? Nominal, right? So you can't really rank married versus unmarried. There's no such thing as married and a half. I guess separated, I don't know, but that's not an option here, and so forth, right? Address is going to be nominal, income is going to be ratio, and so forth, and you can actually change their characteristics. For example, the variable view under age, so it just says numeric here because SPSS isn't nuanced enough to distinguish between ratio and interval. Is it a number or is it words? And you can say it takes up 4 spaces in my data set, and here's a label. The label comes into play when I run an analysis. The output, instead of saying age, it'll say age in years. You can put anything you want in here, and so forth. So you can go through. Like here, gender is a string. String in computer words means words. This means words. So string would be a name. So you can't do math on strings except count the number of times things occur. Right? And at the bottom here, you can switch back and forth between your data view and your variable view. You'll see all this on Monday. Now, there are all kinds of versions of SPSS. I think we have the most recent one in the labs. The most recent one is like version 21. The ones in the textbook were created using version 16. Doesn't matter. It still works. In fact, it's probably better because you have older versions are less complicated. Right. So look at this. This is a histogram. No, it's not a histogram. Sorry. These slides should be animated. I don't know why they're not being animated right now. So all the information is coming up all at once. It should be kind of, I would ask, what is this? And you say, I don't know. And I'll say, oh, it's a frequency distribution. Oh, come on. But it didn't do that. So now you know what it is. It's a frequency distribution. Is that the same as a histogram? Have you heard the term histogram before? You must have in high school, yeah? Is that the same as a histogram? Obviously, yes. Yeah, very good. Look at you. Well done. That's correct. So in this particular case, this is not a histogram. What gives it away is technically a histogram, the bars touch, right? Technically. So we're going to talk right now about frequency distributions. So this is one example of a graphical depiction of a frequency distribution. In this data set, let's say the data is people's ages. In this data set, we have one person who's 5 years old. We have about 3 people who are 15. We have about 7 people who are 25. We have about 20 people who are 35, and so forth. So it's a way of showing the frequency of how many times data appears in my data set. How often do I get 45-year-olds? How often do I get 75-year-olds? That's all it is. And this is deeply important. So it sounds so simple, how often do certain things pop up, but it's the first basic kind of statistical analysis, and it informs a whole universe of different kinds of analyses. So a frequency distribution is a systematic arrangement of data with a count of how many times each value occurred. That's from the textbook, right? And you can show this in many ways, a table, a graph, a list, or so forth. So here's a list, 1, 2, 3, 4, and 5. You can count the number of times it comes up. Right. So the number of times something comes up, you sum them all up, you should get n. N is always your sample size. N is always how many people you've got total. Small or large. This textbook likes large n. Okay. And F is usually frequency. So a typical frequency distribution has these following characteristics. The actual data values, right, 15, 7, 5, whatever it might be, how many times they occur, a relative amount of how many times they occur. What's that? That's a percentage. You know, 45-year-olds account for 25% of my sample. The cumulative relative frequencies, what's that? That is, as I progress through my list of data counts, how many more are added on. So if I'm ranking my ages, I've got 2% are 5 years of age. 3% are 10 years of age. That's a total of 5%. So 5% now account for 5 and 10 years of age. Next one down. 10% of my sample is 25. I add that to my previous 10%. Now 20% is 25 plus. So as you see, as we go through our data, through the ordering of our data, we add up the percentages as we go. Why is that important? It allows us to say, from this point on, I've accounted for 75% or 80% of my data. You see what I mean by that in a second. So here is an example. We have 10 people of varying ages. Here are their ages, 17, 26, 33, etc., all the way to 19. And we are going to create a distribution for their age groups. Why their age groups? Why didn't I just create a frequency distribution for their actual ages? Exactly. How many 17-year-olds do I have? I got 1. How many 26-year-olds? 1. 33-year-olds? 1. I got 1 of everybody. That tells me nothing. Right. Now, remember I said last time, it's always dangerous to go from continuous to categorical. Here's an example where it's useful to go from continuous to categorical. As we compress our data into groups, we're going to learn some things about how they are distributed. So, age group is from 0 to 25. I've got 1, 2, 3, 4. 4 people, right? Again, this should be like an animated slide where this number pops up, but it doesn't. Okay. From 26 to 45, I've got 1, 2, 3, 4. 4, that's right. 4. And over 45, I should have 1, 2, 2. Yeah, there it is. So out of 10 people, That's my distribution. I have 4, 4, and 2 in my frequencies. So the relative frequency is the amount of these guys over all of them. So 4 out of my 10, 40%, are less than 25. Another 40% are between 26 and 45. And the remaining 20% are over 45. Pretty straightforward, right? Now, these are ranked in terms of lowest age to highest age. So as I accumulate them, the first row is to 40%. The second row, combine the two, is 80%, or these two, and the total is 100%. So the cumulative frequency is just adding them up as they go and keeping track of the accumulation of frequencies. Right? And this is a summary of how it looks. Okay. Now, if I wanted to graph or tabulate this in such a way that it's visually appealing, I could create easily a bar graph, and this would be my x-axis, and either one of these two could be my y-axis. If I they have the same kind of shape, right? So now let's look at this from the perspective of our measurement levels. Remember the levels were nominal, ordinal, interval, and ratio. Remember that? I'm going to ask you again, what's a nominal level? What does that mean? Somebody tell me, what's a nominal level mean? I know you know. I'm being really pedantic by asking you to tell me, but I got to make sure you understand. Nominal level, nominal measurement. What's a nominal measurement? I'm not going to go until someone tells me. Yes. It's a name. It's a name. You can't do math on names. Okay? What's an ordinal measurement? Yes, ma'am. A ranking, so integers of ranking, and the quality that distinguishes an ordinal from the non-ordinal ones are that the things in between have no meaning. So between 2 and 3 is not the same as between 5 and 6. We can't be sure that the distances are the same. And interval and ratio we mentioned last time. Sorry, you're saying? Interval and ratio are continuous numbers in which the things in between have meaning, but ratio has a real zero and interval doesn't. And a real zero is a zero that has meaning in the real world, like height. Being 0 inches tall means something. Being 0 degrees Fahrenheit doesn't mean anything. It was made up by people. Okay, so frequency distributions, we can construct them for any level of measurement, but some are preferred to others. For example, for categorical levels, for nominal level, we cannot do cumulative frequencies. Why can't we do cumulative frequencies if our data is a nominal? Yes? Exactly right. There's no way to rank them. There's no progression. For example, if I asked you what province were you born in this room, and let's assume you're all Canadian, you're all born here, let's assume that, and let's say 5 of you are from Manitoba, and 6 are from New Brunswick, and 10 are from Quebec, and so forth. So I've got data. I can show you the frequency count in each province. I can't really rank it, right? I can't say, well, I can make up an arbitrary ranking. I can go from west to east, or I can go from alphabetical, but I'm imposing an artificial rank at that point. I've introduced a new variable there, geography or alphabet. Whereas in pure numbers, there is an innate ranking. How old you are, there's an innate ranking. Anytime I attempt to rank or order words, I'm attaching a human quality, which introduces a new level of bias, and we can't do that. So cumulative frequencies have no meaning with nominal variables. So, and as we mentioned last time, sometimes it's wise to create categories from continuous variables. So here's an example of weight, people's weight, and the numbers are so small that we would prefer to group them, right, like that. Same thing. So here are my raw data. I've now grouped them into groups instead. So we call this group frequency distribution or just frequency distribution. I won't distinguish between the two. So look at this visually for a second. Here's our data, right? That if we had to visualize how that looks on a graph, it's kind of flat. This, you can automatically see, even visually, that most of them are going to group around the 126 to 175 range. So most of my respondents here are that heavy. Right? I wouldn't know that from looking at this data. I know that right away by looking at even this table. Right? So one way to report a frequency distribution is through a table. We can do it through text. We can say, hey, 38% of my participants were male or had that weight, or whatever it might be, or in a graph. So let's go through some graphs here. The bar graph you know about from grade 3. Everyone knows about bar graphs. But bar graphs have a lot of utility, and of course, we like them to be horizontal when we do frequency distributions. We like the categories to be the x-axis and the frequency to be the y-axis. And it's going to be the relative frequency will be the y-axis, not the raw frequencies. Right. Here's an example. Okay. Note the bars do not touch each other. So this is a case of marital status. What kind of measurement level is marital status? Yeah. It's nominal, exactly. Right. Now, if they were to touch, I've been implying that there is some meaning between the two. That somewhere between divorced and widowed, for example, there is meaning here. There isn't. Either you're divorced or you're widowed, or one of these two. There's nothing in between. There's no other style of marital status that we've accepted in this data. Yes? Right. So one assumes that in this study they have made the decision to distinguish the two. Right. So that's true. So that kind of nuance will have gone into the decision making before you collected the data, if you're a good researcher. And most people are not good researchers. They often forget that little nuance. But yeah, so we assume they are good researchers, and when they collected the data, they will have told people, choose which of the following best describes your situation. And then they'll give a definition of each situation. Single is if you are currently not married and never have been married. Okay, that kind of thing. So let's assume they've done that. But you see here that they are separated because we assume there's no meaning in between them. Now, pie charts, everyone loves the pie chart. So I recently published a paper using pie charts, and it was really exciting because my co-authors, all she cared about was, we finally get to use pie charts in a paper. Because we've been doing them since kindergarten and never get a chance to actually use them in science. It's very rare. So it's really exciting. So the rules of pie charts are simple. All the pieces of the wedges add up to 100. We like them to be, again, the relative frequencies, not the raw numbers. And you begin at the 12 o'clock point and you move clockwise, like this. So you start with the largest wedge first from 12 o'clock and you go around. Our biggest piece is there, second biggest there, third biggest there, and last there. So suddenly, visually, you can see the cumulative frequencies quite well. You can see that a good 72% of my study is either married or single. Right there, that's a cumulative frequency. A good 82% of my study is either married, single, or divorced. That entire thing is a cumulative frequency. So visually, we have a lot of information coming at us quite quickly. That's what makes it so useful. The last is the histogram, and this is the most commonly used of the techniques, and it leads us into doing all kinds of fancy statistics later on. So you've heard the word before, and hopefully you've done some work with histograms. If you haven't, you will now. So it's like a bar graph, but because the x values are continuous, the bars touch to imply that they are in fact continuous. And the days are ranged from lowest to highest, and it looks like this. Now, here I've got the number of people who are 55. This is heart rate data. It's the number of people with heart rate 55 beats per minute, number of 57, and so forth. You can probably tell as I collapse these numbers into categories, the shape of a histogram will begin to change. That's the beauty of a histogram. It's kind of fluid. I can create new groups, and these groups are called classes. I can create new classes in here to compress or expand my histogram. The shape of the histogram is important. I can look at this right away and I see that most people, well, not most people, but commonly the common response tend to be 66 or 67 tends to be heart rate, resting heart rate data. If you're above that, you're probably not normal. If you're below that, you're probably not normal in some ways as well. So the information gets to us very, very quickly. It also shows us there's a skewness in one direction. Right? If you're at this end here, you're kind of an outlier. That word outlier we'll revisit in a week as well. It's an important word. So a lot of information is being conveyed in this histogram right at you very fast. We're going to be working with histograms. One very particular histogram, a very famous one, that's critical to the foundation of about half of all statistical tests to discover more. So related to histogram is a frequency polygon. And really, it doesn't matter. Yeah. It's the same thing, in my opinion. Instead of bars, you use a line, and instead of a flat top, you use a point. And it looks like this. The same data you saw before. And note the distinction here is that you bring it down to 0 at one end. If I go back, this one doesn't go to 0. This one does. So the reason a polygon is preferred by some people is for continuous data is that it really shows us that it is continuous. That there's meaning down to 0 and so forth. And you know that thing on top here, if it was a bar, that flat part is a little misleading. It implies that for those, all the people over here, this is the same frequency, and that's not really true. So this is probably more accurate. Doesn't matter. So when we are describing these distributions, like this one or that one, there are 3 characteristics I want us to think about. And they are modality, symmetry, and kurtosis. You've heard the first 2 words before. You probably haven't heard the last word before. So let's go through what they mean. Our modality is how many peaks there are in your sample. Now you've heard the word mode. We're going to go over mode again in a couple weeks. What's a mode in mathematics or statistics? Remember that from grade 11? The mode. Mode. Nobody remembers the mode. Yes. The most common value, absolutely. Now, there are several values that are common, right? So that's multimode. Right? Multimodal. Sometimes there are 2 values that are common. That's bimodal. So the word mode comes from this, from modality. It's if you look at a distribution, the most common ones will have peaks. And the least common ones will have values and peaks. So the modes are the peaks. Right? So what we looked at so far is a unimodal distribution. That's unimodal. There's like 1 peak here. And the mode here would be about 66. It's possible to have bimodal and sometimes multimodal. Why do we care? Right? Here's an example. Here's a unimodal distribution. Here's a bimodal distribution. You know what that looks like. And why is it useful? Any idea why this would be useful in medicine in particular? Nope. Nor should you. It's a bit of a leap. Okay. Look at this. This is actually a photograph of my friend. I won't mention her name on the YouTube clip. She's a prominent oncologist, and she travels a lot in the developing world, and that is a reaction to a tuberculosis test. We call it an induration. So here's a slide. So an induration is the reaction to the purified protein derivative, the PPP test, as we test for tuberculosis. If you get a raised area after the injection of PPD, then we say you have an induration reaction and you're probably tested positive for tuberculosis. The thing is that the width of the induration matters. There's some people who get a reaction who are not testing positive for TB, and that width is smaller. Right? Now, I forgot why that is. It's an allergic reaction, maybe. I don't know. So we had to figure out which is the width of the induration that actually determines whether or not you have TB versus the width that determines whether or not you actually don't have TB. How can we make a cutoff? Because a doctor needs a cutoff. Oh, you got like 1.5 centimeters here. Clearly, you've got TB. So how do these diagnosis cutoffs come about? Well, it comes off like this. We do this to a lot of people. And after a while, you get enough data that the frequency distribution of the induration response looks like this. This is the number of subjects, and this is the diameter of the induration. So a bunch of people have like nothing, and a few people have like 1 or 2, 3 millimeters, but then this bunch of people have TB. They got real induration responses. And you can see that the majority of them fall around over here. We can make a cutoff, probably a cutoff over here, to be as inclusive as possible, and say that if it's less than 6 millimeters, it's probably not TB. If it's over 6, it probably is TB. There it is. So a simple frequency distribution of people's induration responses over a large enough population, and this is like 400 or 500 responses, gives us a diagnostic criterion for determining whether or not you have tuberculosis. That's how it's done. That's how a lot of these cutoffs are made, by this kind of analysis. What if you only have one mode? It's convenient that the TB response is bimodal. So that's convenient. But a lot of things aren't. Here's one. This is systolic blood pressure. You've learned about systolic blood pressure, I assume, right? Systolic versus diastolic. So we often wonder, what is healthy systolic blood pressure? If you look at the population, that's the distribution. That's it. So most people seem to be around here. So we figure that must be normal. That's it. there's no actual deeper physiological reason for why we think 120 is normal. It's just that most people are there. So we figure that must be normal / healthy. And if you're over 120, well, you're probably not as normal as these people. If you're less than 120, you're probably not as normal either. So diagnostic criteria based on distributions, and often very little else. I'm being a little facetious. This is based on more science than this, but it begins with this. Right? Okay, that's modality. Now let's look at symmetry. We know what the word symmetry means. Symmetry means the two halves are the same. Right? So this clearly is a very symmetric distribution. It might not have been. We could have had a bit on this side that's different from that side. So there are two kinds of ways to be asymmetrical. You can be skewed in one direction or skewed in the other direction. In my opinion, the two definitions look opposite to each other. It's not natural. So a positive skew has a trail that trails off to the positive direction. A tail trails off the positive direction. To me, it should be the other way around. It should be, if you're positive skewed, the bulk of the data should be in the positive direction. That's not the way it works. So keep this straight. If it's a positive skew, the tail skews off in the positive direction. If it's negative, the tail skews off in the negative direction, like so. Right? Positive meaning higher numbers, negative lower numbers. This is a positive skew. This is a negative skew. Do you agree it should be opposite? To me, that confuses me all the time, but that's the way that we do it. All right, so keep that straight in your mind. There is a skewness index, so some things are more skewed than others, and the index goes from 0 to 1. 0 means perfect symmetry, and positive 1 means skewing to the right, and negative 1 means skewness to the left. Excuse me. So how we define whether or not something is skewed is by this definition here. The skewness index is less than twice the value of a standard error. You don't know what a standard error is yet. You will in a few weeks, so just keep that in the back of your mind. SPSS will compute a skewness factor for you automatically. When you choose the distribution function, it'll compute this automatically for you and determine, is your data truly skewed? You're never going to get perfectly symmetrical data. It's a little bit skewed, So we have this definition to say whether or not we consider it to be functionally skewed or not. Here's some examples. So this one has a skewness index of 0.8, right? It's skewed to the positive direction, right? And this is the standard error. Don't worry about the number here. So remember the definition here is less than twice the value of a standard error. This twice the value is 0.66. This is more than twice the value. Therefore, this is skewed data. This one here is skewed the negative direction, 0.72. The standard error is 0.34. Twice that is 0.68. 0.72 is more than that. The absolute value is more than this. So we say that's skewed as well. Okay. So that's a couple of examples. Right. That takes us to kurtosis. I'm going pretty fast here. Should I pause? Any issues around skewness? We're cool. Kurtosis is the degree of flatness of the distribution. And there are three words you're going to learn. They are leptokurtic, mesokurtic, and platykurtic. Right? So you know what a platypus is? The cute little Australian thing? It's called a platypus because it has a flat tail. Because plat means flat, like a plate. That's why it gets its name. So when you think of platykurtic, think of the platypus. It means it's flat. Lepto means thin, so it's a very thin peak. And meso is something in between. Simple as that. Lepto, meso, plata. Right? So, and like skewness, there is an index that we compute for the degree of kurtosis. We like it to be mesokurtic, to be ideal, like right smack in the middle. So here's an example. This is a leptokurtic index right here. This is platykurtic. It gets flatter. Right. So this is a very famous frequency distribution. In its ideal scenario, it is mesokurtic, it is symmetrical, it is unimodal. It's called the normal distribution, and it has other names too. Have you heard of the other names of this? The bell curve is one of them. Anything else? Yeah. It's also called the Gaussian distribution. Gauss was the greatest mathematician who ever lived, and I'll tell some Gauss stories later on. So Gauss did a lot of stuff with this, and other people discovered this. Then Gauss had this thing where he would, every time a discovery came up, he'd go through his records. Oh, I did it already. Simpsons did it, or whatever. I did it already. So he kept doing this over and over again. So, fine, Gauss, you discovered everything. So he discovered this too. So this is the Gaussian distribution, the normal curve, the bell curve, whatever it might be. We tend to call it the normal curve. I tend to call it a Gaussian distribution. So it's a unimodal symmetric reflection. And it's really important in everything we're going to do in inferential statistics. By the way, there are two large universes of inferential statistics. They are called frequentist and Bayesian. You're not going to hear the word Bayesian ever again, probably in your university education, unless you pursue advanced training in statistics. But I want you to know about it. And maybe I'll mention some things about Bayesian later on, because Bayesian really is what the experts use now. But the frequentist school is what we are learning here. Frequentist school is based on frequency distributions. The entire history of statistics comes out of frequency distributions, using frequencies, histograms, Gaussian distributions, to elicit wisdom about the ways that other things are distributed. The Bayesian method is quite different. Won't go into this now, but it's pretty cool. And I'll tell you a story at this time later in the year about a particular game show that gave credence to the Bayesian methods. The Let's Make a Deal, it's called. In fact, if you Google the Monty Hall problem, it's a classic example of Bayesian statistics, of how to win Let's Make a Deal every single time using Bayesian statistics. Off on a tangent. The thing about the normal distribution that's so important is that it pretty much describes the distribution of every human characteristic. Every human characteristic you can imagine, if you get enough people and measure them, will fall along that distribution. IQ. Yeah, if you measure enough people's IQ, you're going to find that most people fall smack in the middle. A few are better, a few are worse, a few are really smart, a few are really dumb. Right? And if you graph it, it looks like that. Height. A bunch of people are smack in the middle. A few are taller, a few are shorter. A few are giants, a few are tiny. Just like that. Every human characteristic falls along this curve, and we can modify that curve, make it skewed, less skewed, transform it. And that allows us, when I measure characteristics of your sample, I can compare it to the normal distribution of the entire human characteristic and say where you fit on that scale. And that tells me whether or not your situation is less or more probable than the truth. And that's all we're ever doing. That's all we do for the rest of every test we do in this class, is determining whether your situation, what you measure, is less or more probable than what's really going on. That's all statistics is. Isn't it amazing? It's magic. I've summarized the entire degree for you in one sentence. So here it is. So here's a really bad example of a normal distribution. Here are a bunch of people who are tall. We've got some guys really tall in the center and some less tall. There it is. So one short person, one tall, three medium people. There. And it's, I hate telling the story about Hadul anyway. So the thing about the normal distribution is, because it describes every human characteristic, it means that for every human characteristic, there's always going to be somebody at the extreme end. There's always going to be one or two freaks doing freaky things that will stun you. How is this is not scientifically possible? But it is, because there's always, if there are enough people, there's always going to be a couple of extreme outliers. For example, do you know how old the youngest mother on record is? The youngest human mother? Yeah? 5, that is correct. There's a Peruvian woman, girl, right? It occurred earlier in the 20th century, and she gave birth to a boy who was raised as her brother and into adulthood. And no one knows who the father was. But the thing is, she was born essentially going through puberty as she was born, right? So that's an extreme biological situation. How is it? It's not magic. It's just that she lay along the extreme end of normal distribution. So this describes the age of puberty for women. Most people will hit puberty around age 10, 11, 12, around here, right? A few will wait later, a few will be earlier, but there's always going to be one because they're really early. That's her. There it is, all right? So that's the magic of normal distribution. Okay, so the beauty of frequency distributions is that it's the first step in understanding your data. Once you collect data, you plot some curves. You see how are things, do I have outliers? What are most people? Are most people in puberty at 10 or 15 or whatever it is, right? So we look at this to get a feel of the data. We can also see how clean the data are. And by the way, data is plural. Datum is singular, right? The data are clean. So we'll discuss what clean means next time. Clean usually means something like how many are missing, things like that. Okay, we're going to look at more later on central tendency. Central tendency is how much of the data tends to be clustered around its center. And there are three measurements of central tendency: mode, median, and mean. And of course, you learned all about that last time, but we'll go over it more in depth. This is your homework. Go forth and be fruitful. And we'll see you next time. Bye, YouTube people. Oh, we got one live viewer. Wow. Cool.